Okay, so this is the midterm review for midterm 2 for EGME 417 in the spring 2021. All right, so I looked at the poll on Canvas, and these were the two, overwhelmingly two most requested topics that I cover. And so the first one, by about 90-something% is 2D diffusion with FVM. I guess that's not too big a surprise. And the second one is explicit time margin. Okay. All right, so for this review, I'm going to do most of the time on the first one because I think everyone wants to see that one. And then I'll do a little bit more on explicit time margin, maybe about 20 minutes at the end. Okay, so let's start with 2D diffusion with finite volumes. All right, so 2D diffusion problems, you know, it's nothing nothing too new to us, but I think the new thing here is doing it with finite volumes. Okay, and so you know, as we're going about these derivations, I know the method itself is very different, but you know, don't forget everything that you learned about diffusion when we did it with finite differences. Okay. All right, and so I'm going to go through kind of the whole process here, and I'll give it a little bit of a different treatment than what I did in the lectures. So I think you know this way might make a bit more sense when we treat each integral individually. Right? All right, so let's start with our general equation. Right? And so we have minus k times divergence of the gradient of phi, right? And this is equal to q of xy. Right? And just like we always do with, you know, with finite volumes, what we're going to do is we're going to integrate this. Okay. And then what we do from here is we take this left integral here, which is in kind of the perfect form for a divergence theorem, and we're going to convert it using that. Okay. And so we perform that conversion. What we get is minus k integral around the boundary of gradient of phi dot product with the normal vector ds, okay? And this is equal to second integral or double integral of our source term. Okay, and so I'm going to focus the majority of this time on the second term right here, okay? Because that's kind of, you know, where most of the magic happens. Okay. All right. So that term is basically, you know, kind of like as we always see, if we have kind of our square domain right here, right? That term is essentially going to be, we're going to travel around the boundary or around the outside of our cell. Okay. Around the outside, okay? And then we're going to integrate across these four different lines right here. Right? And so we're going to integrate off this line in green, then integrate on this line in red, then this one in blue, and then this one in orange, okay? The key here is that, you know, we're only going around the outside. Right? The other key to note here is that, you know, since it's hard to kind of go around or integrate around the sharp corners, what we do is we split this integral into four different ones, okay? One for each face of the cell. And so what we're going to get in the end is four different integrals for that, right? So we're going to start with this, right? And so we have integral around the entire boundary here of gradient of phi dot product with n, okay, ds, okay. And then we're going to break this into four, right? And so I'm going to start up top and then kind of work my way around from there, right? And so we're going to start on the integral on the north face of gradient of phi dot product with n ds, okay, plus plus on this side, plus integral on the east face of gradient of phi dot product with n ds, okay, plus integral on the south side, gradient of phi dot product with n ds, okay. Then a squeeze west integral down here, gradient of phi dot product with n ds, okay. And so now what I'm going to do is I'm going to evaluate each of these integrals individually, okay. And so I think, you know, for this, it's good to kind of keep things separate, just so that, you know, we can go and you know, kind of manage each one individually. Because I think once everything is combined, it gets a little bit hard, especially when you're applying the boundary conditions. And so this is going to be a little bit of a different treatment than the lecture notes, because I'm keeping these separate. But, you know, I think this makes things a little bit easier once you're you know, when you're applying the boundary conditions. Okay. All right, so actually let me go ahead and erase this because I want to stay on this page, okay? And at this point, you know, we need to evaluate this expression right here, right? So the gradient of phi dot product with n is going to be different on every single face of the square, okay? All right, so let's start with gradient of phi, right? And so gradient of phi, remember, this is basically the partial derivatives of phi in each x and y directions, right? And so it's basically a vector where it's partial phi partial x for the x component, and then partial phi partial y for the y component, okay? And then the n hat here, this is the normal vector on each of the faces, right? And so basically the way you do that is you draw just a line that's perpendicular to the face, and then just whatever direction that line is facing, that's your normal vector, right? And so for example, for the north face here, you know, we have a vector that's going straight up, and so that's going to be 0, 1 for the north face, okay? For the east face, we have the arrow pointing to the right, and so that's the vector 1, 0. Okay. For the south face, that's going completely down, so it can be 0, 1 for the south face. Okay. And then for the west face, it's pointing to the left, and so we have -1, 0. Okay. All right. And so now, you know, the goal is for each of these faces is to take our gradient of phi and then dot product it with the normal vector. Okay? And so I'll do one just quickly for the north face here, just so you can kind of see. Okay? And so for the north face, we have gradient of phi, which is partial phi partial x, comma partial phi partial y. Okay, dot product with the normal vector for the north face, which is 0, 1. Okay. And then we're just going to perform just kind of a regular dot product here. And so we're going to take the first components here and multiply them with each other. And so we have d phi dx times 0 plus the second component d phi dy times 1. Okay. And so, of course, you know, d phi dx times 0 is just 0. And then we're just going to left with d phi dy. Okay. Positive. Okay. All right. And so if we apply that dot product to every single integral here, then what we get is the following. So for the north face, what we get is just like what I just did. We have d phi dy, okay? And since this integral goes from left to right here, we're going to do d phi dy dx, okay? Okay, for the east face, we're going to have d phi dx. That's what results from the dot product. And then the integration direction is y, and so we're going to do dy here. Okay. Next, we have the south face, and for the south face, we have a -1 dot product with gradient of phi, and so we have a minus integral d phi dy dx. Okay, and then for the west face, we have a minus integral d phi dx dy. Okay. And so far, so good. Okay. And so now this is kind of a much more of a manageable thing to integrate, because now instead of having these weird nablas and weird dot products here, we've evaluated that dot product, and now we're working with, you know, something that's reasonable. Okay. All right. And so from here, what we do is we're going to apply our other integration rule known as the trapezoidal rule. And so for the trapezoidal rule, what we do is we approximate these integrals by taking the integrand, okay? And so the integrand here being the whatever the function was inside, okay? And so the integrand for this first one is d partial phi partial y, okay? And then we multiply it by the size of the integration domain, okay? And so in this case, is because it's, we're doing a 1D integral here, we're going to multiply by the length of that line. And so the length of that line is delta x, okay? And then the other thing that we have to put here is a little subscript of n, okay? And so that tells us that we're evaluating this integrand here on the north face, specifically at the centroid of this north face, okay? That's what the trapezoidal rule says, is that we evaluate things at the centroid of the integration domain, and we multiply it by the size of the domain. All right, and so if we apply that same thing to all of these integrals here, okay, we have d phi dx at the centroid of the east face times delta y. Then we have a minus partial phi partial y on the south face times delta x, okay? And then we have a minus partial phi partial x on the west face, delta y, okay? And so now we have, four different, integral expressions here where, we've evaluated these things on the faces, okay? And so the next step that we have to do here is now that we have the equations in this form, right, where these guys here are the derivatives evaluated at the face, okay, that's what all the little subscripts there indicates, that these derivatives here are evaluated at the face, okay? And so we don't want to evaluate these at the face. And so what we want to do is we want to evaluate these in terms of the centroid values of the cells. Okay. And so let's go ahead and do that on the next page. And before I forget, let's not forget here that we have k's that need to have all the way here. So we should have k, 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 k. Okay. And so it's getting a little bit messy here. So let's go ahead and do that on the next page. Okay. All right. And so the next step in the finite volume process, and this is true for both diffusion and convection, although convection is not on this exam, okay, is we want to put the face values in terms of the self-center values. Okay. And so let me go ahead and write out our four integrals again, and and I'll put them in the current form in terms of the face values. Okay. And so we have integral on the north of let's see. We have integral on the north of partial phi partial y dx. Okay. And so right now the form that we have for this is partial phi partial y on the north face, delta x, okay, times k. Okay. And we have k, east face, partial phi partial x dy is equal to k, partial phi partial x delta y, okay. Next we have k, minus k, sorry, minus k integral from on the south face of partial phi partial y dx. Okay, this is equal to minus k partial phi partial y delta x. Okay, we have minus k on the west face partial phi partial x dy. Okay, and this is equal to minus k partial phi partial x delta y. Okay. All right, so here are our four integrals, and then now we want to put them in terms of the cell-centered values. Okay. Okay. And so basically what we're going to do here is that because we have these derivatives here, okay, all we're going to do here is we're going to use a finite difference approximation for each of the integrals, okay, or for each of the derivatives. All right, so let me go ahead and draw kind of a small version of what we have. Okay. Right. So it's very tiny, but you can see that, you know, in the middle of this kind of D pad here, we have phi sub c, which is the value of phi at the center cell, okay. And then we have the centroid values for all of the neighboring cells. And so we have phi sub n, and that's the centroid value for the north neighbor, phi sub e, which is the centroid value for the east neighbor, phi sub s, which is the centroid value for the south, and then phi sub w, which is the centroid neighbor for the west neighbor. Okay. All right. And so plugging in a finite difference approximation for these derivatives here, for the north side, what we see is that, you know, we have d phi dy on the north face, right? So let me go ahead and color code this. Okay. And so this guy is going to be on this face right here, right? And so the north face is the one between phi sub c and phi sub n, okay? And so to approximate this derivative, what we can do is we can do, let's see, phi sub big N minus phi sub c, okay, divided by the distance, the vertical distance in between those two, so that's delta y, okay, times delta x, okay. All right, and so we can do similar things for all the other ones. And so for the east face, you're going to have phi sub e minus phi sub c divided by delta x times delta y, okay. We have minus k. Remember, we always put either the rightmost one or the rightmost phi value or the upper phi value first in our finite difference expression, just so that we're consistent, right? And so since this one we're going on the south face, we have phi sub c minus phi sub s, okay, all divided by delta y times delta x, okay? And then we have a minus k, phi sub c minus phi sub w divided by delta x times delta y. Okay. So let me go ahead and color code the rest of these guys. Okay. So this is on the east face. This is on the south face. And this one is on the west face. Okay. Right, and so these are our four integrals. And so, you know, normally what you do is that you would, you know, if you have an interior cell, you would just add all of these together. And so that would give you your expression. But for now, you know, I want to leave these separate, because by leaving this separate, what we can do here is we can very easily apply our boundary conditions, because for the cases where we have boundary conditions, you know, we're going to just substitute in for this expression here. All right, so another thing very quickly we can do is that, you know, if we assume that the grid spacing is the same, we can go ahead and cancel out all these deltas, okay? Right. And so most of the time that's a reasonable thing to do, because it's it kind of simplifies our math a bit. And so you know, this is that's usually a fine thing to do, okay? Okay, and so now we have our four integrals, and we have everything in terms of the self-centered values. And so if you have an interior cell, all you would have to do is just add all of these guys up together, and then that would give you your, you know, the left-hand side of your 2D diffusion finite volume expression. Okay. Okay, so and so there's that. Very quickly, let's talk about the source term. Okay. Or let me write down. So if interior cell all we have to do is just add up all those four integrals together, or the result of those two. Okay. And then by adding all those things up, you would end up with your algebraic expression. Okay. On the left-hand side. Okay. All right. Okay. And so we'll do an example of that later. Okay. But just very quickly, let's do the source term. Okay. And so for the source term here, all we're going to do is we're going to apply just our 2D trapezoidal rule. Okay. All right. And so normally for the source term, what we have is q of xy times dA. Okay. And so to apply the trapezoidal rule here, we're going to evaluate the integrand here at the centroid of the cell, right? And so it's going to be xc, yc. And then we multiply by the area of the cell itself, okay? And so the area is going to be delta x, delta y. But then if we assume that these are the same, okay, then we see this is going to be q at xc, yc, delta squared. Right? Okay. And so now we have kind of two components to our 2D fine volume. So we have our four integrals on the left. Okay. And this is equal to our source term. Okay. All right. And so actually, before we get into the boundary conditions, let me just add up all the four integrals and then show you kind of what you get from that. And also I need to correct a typo here because, there's what we multiply in front here is not positive k, it's a minus k. Right? And so these should all be minuses and these ones should be pluses, just like that. Okay. Okay. And so if we add up basically everything on this column right here, okay, and so let's go ahead and do that. And so we add up the four integrals, what we get is, let me go ahead and list them kind of top to bottom here, just so you can kind of see, right? So we have integral on the north face, integral on the east face, integral on the south face, integral on the west face, okay? I'm just gonna do shorthand here just because, I wanna make sure I get to some time advancement here, right? And so this is going to be a minus k, phi e minus phi c, all right? This is going to be a minus k, sorry, this is north, right? This is phi e minus phi c, right? It's going to be a positive k, phi south minus, or phi c minus phi south, okay? This is positive k, phi c minus phi w, okay? All right. And so if we add all these together, then what we get is, I'll put a minus k out in front, just because that's traditionally how it's defined. Okay. Then what we have is phi n plus phi e plus phi s plus phi w minus 4 phi c. Okay. Right. And so this expression, this is probably the one that you see in the notes. And so, the way that we get this is we just add all four integrals together. Okay. Okay. And so that's the expression for, an interior cell. Now let's talk about what we have to do for boundary conditions, right? And so for the boundary conditions, the way that we're going to do that is we're going to look at which faces of our cell borders a boundary. And for those integrals, all we're going to do is we're going to replace that integral with a boundary condition term. Okay. All right. And so let's go ahead and do that. And so basically, you can kind of think of it as like for each of the integrals that we have, we're gonna have two cases, right? We have a case for if that face is on the interior, and then we're gonna use basically exactly as what we have, or another case is if they're on a boundary, and then we're going to apply that boundary condition. Okay. Okay. And so let's do an example where we have a boundary condition on the south face. Okay. In particular, let's look at a Dirichlet boundary condition. All right. And so, we're going to have a situation that looks like this, right? So we have our cell that's like this. We have our east and west neighbors. Okay. And then on the boundaries here, we have phi naught. Okay. Okay. And so in this situation, because we have neighbors on the east and the west and on the north, we're going to leave those integrals alone. Okay. And so the only integral we're going to change is the south one. Right? All right. So normally our south integral looks like the following, right? And so we have a positive k times phi south minus phi c divided by delta y times delta x, right? And so that's normally what we have for this integral right here, okay? And so what we're going to do instead is that we're going to replace this with a different finite difference expression that incorporates the Dirichlet boundary. Okay. And so we need to modify this because we no longer have a phi south, right? And so we're going to replace this with phi naught, okay? And then since the distance in between, phi sub c and the boundary here is only half the distance, right? Instead of delta y, we're going to divide it by delta y divided by 2, okay? All right, and so after we make that substitution, what we get is 2k. So I'm going to bring this 2, and it's going to pop out in front over here. And we're going to assume that delta y and delta x are the same. Okay. And so you have 2k times phi naught minus phi sub c. Okay. And so this is the new south integral with the Dirichlet boundary condition incorporated. Okay. And so now what we can do is we can add these together with all the other integrals that we had, okay? And then we end up with an algebraic expression. And in particular, because this phi naught is a known quantity, we're going to kick that over to the right-hand side of the equation. Okay. Okay. And so I'll do this kind of in practice, in an example, but I just wanted to show you just kind of what we would do. Okay. All right. And so now let's do a Neumann condition. And let's do an example where we have a Neumann condition on the north face. Okay. All right. And so, we're going to have a situation that looks like this. Okay. Okay. And so just like before, since we have neighbors on the east and the west and south, we're just going to leave those integrals alone. Okay. And then we're only going to replace the north one. Right. And so our north integral now, normally what it is we have a minus k times phi n minus phi c divided by delta y, delta x, okay? But for a Neumann boundary condition, what we're going to do is we're going to replace this entire expression right here with our Neumann value, okay, with gamma. Right? And so in the end, what we get here is minus k gamma delta x. And then from here, just like we saw with the Dirichlet boundary condition, we can add this together with our other three integrals, and then that will give us our expression. Okay. Okay. And so that was a lot of theory. And so let's go ahead and put this in practice with an example. And so let me go ahead and do a little bit of the homework problem. And so this can be homework problem 2B. Okay. All right. So this is going to be homework 5, problem 2B. 5. All right. And so in this problem, we have a finite volume grid. Okay. And so we're going to have 16 cells. Okay. And then our boundary conditions are the following. And so we have phi is equal to 60 up top, phi is equal to 45 on the bottom. Okay. We have a Neumann condition here on the right side and a Neumann condition here on the left side. Okay. And so, let me write out the equation. So the equation is the following, right? And so the equation is minus 5 partial phi, partial squared phi, partial x squared, plus partial squared phi, partial y squared is equal to cosine of pi x minus 2 sine of pi y. Okay. And so from this equation right here, we can say that our k value here is 5, right? And so don't put negative 5 because normally, our diffusion equations have that negative out in front already. And so our k value here is just 5, okay? And our q of xy here is cosine of pi x minus 2 sine of pi y. Okay. All right. And so I'm not going to do all of these cells because that would be a little bit crazy. Okay. But let me just do I'll do 3 different cells here. Right. So let's do one interior cell. So let's do cell number 7. Okay. Let's do one cell with a Dirichlet boundary condition. And so let's do cell 15. Okay. Then let's do one cell with two boundary conditions, right? So let's do cell 4 as well, okay? All right. Okay, so for cell 7, we have neighbors on all sides. Okay, and so if we have neighbors on all sides, then all of our integrals take their base form. So let me go ahead and write out all of our integrals here. Right? And the west face. All right. So if you want to use the shorthand notation here, we have just integral and then north, then I'm going to know what you're talking about. And so you can use this to help save yourself some time. All right, so for the north face, what we have here is a minus k, and so we have a minus 5, okay, times the north neighbor, which is phi 11, minus phi sub c here, which is phi sub 7, okay. Right. Then for the east integral, we have a minus k, and so we have a minus 5. We have a minus 5. Come on, iPad, right? And then we multiply by the east neighbor, which is phi 8, okay, minus phi sub c, which is phi 7, okay. Okay. Then we have the south neighbor, and for the south neighbor, we have k, which is 5, times phi sub c, which is 7, minus phi sub south, which is phi 3, okay. And for the west neighbor, we have 5 multiplied by phi sub 7 minus the west neighbor, which is phi 6, okay? All right. And so now all we have to do is just add all these together. And then that will give us our expression here, okay? All right, and so adding all of them together, what we have is a minus 5 out in front times phi 11 plus phi 3 plus phi 8 plus phi 6 minus 4 phi 7, okay? And I'm just going to leave the right-hand side, generic for now. But for the exam, mostly just because this is kind of a complicated function. But for the exam, I want you guys to plug in for Q, okay? And so we have Q of xc yc delta squared, right? Okay. And so that's cell 7, right? And so that's good, okay? And so now let's do cell 15. Right. And so for cell 15, what we have is a Dirichlet boundary condition on the north face. Right. And so, we're going to adjust that integral accordingly, right? And so let's go ahead and write down our 4 integrals here. Okay. Okay. And so we have integral on the north face, integral on the east, integral on the south, integral on the west. All right. And so let's start with the north integral, right? And so for the north integral, we have to adjust this, based on that integral, since we don't have a north neighbor, okay? And so this is going to be a minus k, okay, times our Dirichlet value, phi naught, okay, minus phi sub c, where phi sub c in this case is 15, okay, all divided by delta y divided by 2, okay, times delta x. And so we can cancel out delta y and delta x because we're assuming they're the same. Okay. Our Dirichlet boundary condition here is 60. And so let's go ahead and plug in that. And then our k value here is 5, right? And so what we get from this is 5 times 60, which is 300, times 2, which is 600, okay? Right? Okay. And then, let's see, and then to this, we're going to add minus 5 times 10, times 2, and so this is minus 20, or minus 10, sorry, minus 10 phi 15. Okay. All right, and so that's the first integral that we have there. Okay. Okay. And so that's the north integral, and so that's changed. Okay. And of course, since we have the 600, which is a known constant, we can go ahead and move this to the right-hand side. Okay. All right, and so now let's go ahead and fill in the east, the south, and the west integrals. And those are just not going to change, right? And so for the east integral, what we have is the east neighbor, and so we have a minus k, so minus 5, times the east neighbor here, which is phi 16 minus phi 15. Okay, right? And that's all there is for that one. Okay. Now we have the south neighbor, and for the south neighbor, we have k times phi 15 minus the south neighbor for 15, which is phi 11. Okay. And then we have the west neighbor, west integral, which is 5 times phi 15 minus phi 14. Okay. All right. And so let's go ahead and add all these together. Okay. And so we add all these together, then let me go ahead and factor out a minus 5. Okay. And so if we factor out a minus 5 and we add all these together, we get phi 16 plus phi 11 plus phi 14 minus 5 phi sub 15, okay? And this is equal to q of xc yc minus 600, okay? And then minus 600 came from this guy up here, and we subtracted it from both sides to do that. Okay, so that's cell 15. And so finally, let's do one of the corner cells here, which is cell number 4. Okay. And so cell 4 here is unique because it has a Neumann condition on the east face. Okay. As well as a Dirichlet boundary condition on the south. Okay, and so let's do the same thing. So let's write out our 4 integrals. Right, so we have integral on the north, integral on the east, integral on the south, integral on the west. Okay, and let's go ahead and write these expressions for cell number 4. Okay, all right. So let's do the integrals that don't change first. And so let's do the north integral. Okay, and so we're gonna have a minus k minus 5 times phi sub 8, which is the north neighbor for cell number 4, minus phi 4. Okay. Okay. Then our west integral here is also unchanged. Okay. So we're going to have a positive 5 times phi 4 minus phi 3. Okay. Right. And so those don't change. But now what's going to change here are going to be the east and the south integrals, because those are where our boundary conditions are, right? Let's start with the east integral. And so for the east integral, we have our Neumann condition, okay? And so if we go by what we know, then we know the boundary condition here is going to be a minus k times gamma, which is our Neumann boundary condition value, times delta y, okay? And so if we plug in for the values here, we have a minus 5 for k. Our gamma value here is 25, okay? And delta y is whatever it is. I'm not even sure what it is for this problem, right? And so this is going to be a minus 125 delta, okay? And so that's the Neumann condition. And of course, this goes to the other side because it's a constant number. Okay? Okay. And then let's do the south side integral now. So for the south side integral, we have k. Normally what we have is we have phi sub south, or phi sub c, sorry, minus phi sub south divided by delta y times delta x, right? But in this case, since we don't have a south neighbor, but we do have a boundary condition there, right? We're going to replace this with phi naught, and it's going to be delta y divided by 2. Okay? The deltas are going to cancel out, and then what we get is a 5 times phi sub c, which is phi 4 in this case, minus phi naught, where phi naught is a 45, okay? And of course, that 45 is going to move over to the other side. Okay? All right, and so finally, let's go ahead and add all these together. And so adding all these together, now if you go minus 5 out in front, okay, be phi 8 plus phi 3 minus, this is 2, sorry. It's not 45, so this is 90, okay? Okay, so this would be a minus 4, phi 4, okay? And this is equal to q at xc, yc, delta squared, okay? Plus 125 delta, plus 5 times 90, which is from this guy right here, okay? All right. And so there's 3 examples for how to apply this 4 integral method to solve your 2D finite volume diffusion. Okay. All right, and so that took much longer than I thought. Okay, and so now let's just very quickly go over explicit Euler time advancement. Okay. And so this is kind of completely switching topics here. And so remember, explicit Euler time advancement. This is the methodology that we use for unsteady problems. And unsteady problems, these are problems that that change with time. Okay, and so we're actually escaping finite volumes here, and so we're going to go back to finite differences. Okay, and so our starting point for this equation or for this method here is going to be our full transport equation in one. Let's do 1D for now. All right, so we have partial phi partial t plus u partial phi partial x is equal to k partial squared phi partial x squared, okay, plus q of x, okay. And so this is our full transport equation where now we have the unsteady term here, okay, right? And so the way that we're going to advance this is we're going to replace each of the derivatives here with an appropriate finite difference approximation. Okay. Paying special attention to the fact that we're now doing a derivative in time. Okay, and so partial phi partial t is going to be phi. Normally we do a subscript here for the space, but since we're doing a derivative in time, we're going to have this be a superscript. Okay. Right, and so this is going to be plus u And then this is just a plain old partial phi partial x. And so I'm going to use central difference for this. Okay. This is phi plus 1 minus phi minus 1 divided by 2 delta x. Okay. This is equal to k times phi plus 1 minus 2 phi plus phi minus 1. Okay. All over delta x squared. Right. And then plus q of x. Okay. So qi. Let's do qi. Okay. And so, the way that we obtain a time marching scheme here is that a time marching scheme is nothing more than just a way to solve for phi at n plus 1. Okay. Right. And so the nice thing about explicit time advancement is that for all the other phis in this expression here, we're going to put a value of n there. Okay. Okay. And so for all the phis that take place in the spatial derivatives, we're just going to evaluate them at time step n. Okay. All right. And so what we have here is kind of a massive, algebraic expression. And so what we can do from here is basically just rearrange the terms, okay? Because we want to rearrange things in so that we can solve for phi of n plus 1. Okay? This is phi I. All right. And so you can look at the details of that derivation in the notes, but I'm going to just give you the final answer here just so that we can start working on an example. And so we have phi n plus 1 is equal to u delta t divided by 2 delta x, okay, plus k delta t divided by delta x squared, okay, phi I minus 1 to the n, right, plus 1 minus 2k delta t delta x squared phi I to the n, okay, plus a minus u delta t divided by 2 delta x plus k delta t divided by delta x squared, okay, phi I plus 1 n, okay, plus qi. And so it's a lot, and so it's a big expression here, but there's only a few actual variables here because the most of them are kind of repeats. Okay, and so what you have to do here is you're going to have to plug in for all the different variables in order to get our time advancement equation. All right, and so let's just jump straight into an example here, just to kind of illustrate this. Right? All right, and so let's do just a very simple unsteady diffusion equation, right? And so we have partial phi partial t is equal to 3 partial squared phi partial x squared, okay? Okay, and then let's write down the boundary conditions. Right, and so the boundary conditions, let's say that our first one is going to be a Dirichlet boundary condition, right? And so we have phi at 0. For all values of time, this is going to be equal to 1, okay? And our second one here is, let's say that we have d phi dx. So we have a Neumann condition at x is equal to 1, comma t, and this is equal to 2. Okay. All right, and so let's use explicit Euler, which is the equation that I have above, and solve for the time evolution equation. All right, so first thing we're going to do is that let's go ahead and set, plug in all the parameters here, right? And so in this problem, it's given to you that you're going to use a delta t of 0.1, okay? Also a delta x of 0.25, okay? And from this problem, we can see that k is equal to 3, okay? And u is equal to 0 because convection is not present. Okay. All right. And so plugging all of those in, what we get is phi I n plus 1 is equal to 4.8 phi I minus 1 to the n power, okay, minus 8.6 phi I to the n, okay, plus 4.8 phi I plus 1 n. Okay. Right, and so that's our time evolution equation for this guy. Okay. And at this point, let's kind of remind ourselves what the n and the n plus 1 represent, right? And so the n, remember, that represents the solution at the current time step, which is known, okay? Okay. And so, for the first, you'll see for the first solution for this, we're going to plug in our initial condition and then get that solution from that. Okay. Whereas the n plus 1, this is the solution at the next time step. Sorry, I want the sweat off my hands. Okay, and so the solution at the next time step is unknown. This iPad is so frustrating sometimes. Okay. And so, given a known solution here, you can use this equation to solve for the unknown one at the next time step. Okay. All right. So let's go ahead and do that. But before we do, we need to get our time evolution equations for the boundary conditions. All right. And so our boundary conditions here is we have one Dirichlet boundary condition. So that's fairly simple. Okay. And so the Dirichlet boundary condition is going to be on phi 1. Okay. And so what we have is phi 1 is equal to our Dirichlet value, which is, was again 1. Okay. And to turn this into a time evolution equation, all we have to do is that we say that phi 1 at n plus 1 is equal to 1. Okay. Right. Super easy. And so the next time evolution equation that we'll do is for phi for the Neumann boundary condition on the right. And we're going to assume that we have 5 grid points. I think maybe I forgot to mention that, but we have 5 grid points here. And so the rightmost grid point here is going to be phi 5. Okay. And so for the Neumann BC, just like we usually do, is we're going to do a finite difference approximation. Okay. So we have phi 5 minus its closest neighbor, which is phi 4, divided by delta x. Okay. And this is equal to its the Neumann value, which is 2 in this case. Okay. And then to turn this into a time evolution equation, we have to assign a time index to each of these guys, right? And so for phi 5, we're going to have n plus 1. And then just to make sure that we have kind of a closed form expression, we're going to evaluate phi 4 at time step n. Okay. Okay. And so if we solve this equation for phi 5 n plus 1, what we get is equal to 2 delta x plus phi 4. Okay. Right. And so now that we have the time evolution equations for nodes 1 and 5, for all of the interior nodes, we can just use the same equation that we have on the previous page. So I should say maybe not time evolution, but maybe the explicit Euler equation. Okay. And so that's going to be nodes 2, 3, and 4 in this case. Okay. All right. And so once you do that, what you can do from there is you'll have 5 equations. Okay. And then usually the best thing to do is to take those 5 equations and put them in matrix form, just because it just makes things a bit more convenient. Okay. And so if you put those 5 equations in matrix form, what you get is we have our 5 phi values here, and this can be evaluated at the time step n plus 1. And this is equal to the following matrix. Okay. And so those are the coefficient matrices. That's the coefficient matrix, and that multiplies by a phi vector. Okay, the phi n vector. And so this is phi 1, phi 2, phi 3, phi 4, phi 5 at n. Okay, and then we're gonna have one more vector here for kind of the extra stuff. Okay, and so this is all the terms that didn't multiply by a phi term. Okay. And so here is our matrix set of equations for the explicit time advancement for this problem. Okay. All right. And so this system right here is very unique compared to a lot of the systems that we had before, right? Because normally, we have a matrix set of equations like this, but usually what we're trying to solve for is this one right here, okay? Which is the matrix, the vector that's multiplying by the matrix. And so in order to solve for that, we basically had to do matrix inversion, or in other words, we had to solve a linear system of equations. Okay? We don't have that in this case. And so the thing that we actually want to solve for is actually on this side of the equation, which is all the phis at n plus 1s, right? And so to obtain this, we don't have to do any matrix inversion for this at all. And so all we have to do is just perform matrix multiplication. Okay. Plus a vector addition. Okay. And this is significant because matrix multiplication is no big deal at all, right? And so, for a computer, it does it like that, like it's like nothing, right? Vector addition is kind of the same thing. And so this is one of the really nice features of explicit Euler time advancement in that, there's no linear system of equations that need to be solved at all, okay? And so you just do matrix multiplication and vector addition, which is easy peasy lemon squeezy. Okay, it's not it's not difficult lemon difficult, right? And so this is nice, right? And so just to kind of show you this in action, let's take this set of equations and let's advance it forward 2 time steps. Okay. All right. And so let's see. And so let's start with the 0 initial condition. Okay. And 0 initial condition means that all the phi i's at n, these are all going to be 0. Okay. And so let's advance this forward for the first step. Okay. And so for the first step, what we have is all these phi i's at n plus 1. Okay. That's going to be equal to this matrix, right? This is a 1. This is 0, 0, 0, 4.80. Okay. If our initial conditions are all 0, then all of this guy's phi i's at n, all this is going to be 0. Okay. And then plus 1, 0, 0, 0, 2 delta x. Okay. And I guess 2 delta x in this problem is 0.5 because delta x we assumed is 0.25. Okay. Okay. And so actually this is everything at the first time step. Okay. Okay. And so all we have to do is to solve for the solution after the first time step is just perform this matrix multiplication, right? And so we have all these guys times 0, which is just 0 all the way around. And then we have this guy on the right, okay? And so after one time step, our solution is, so this is phi I at 1, okay? It's equal to 1, 0, 0, 0, 0.25. Okay. Okay. And so, because we started at a 0 initial condition, this is usually not that bad. Okay. All right. And so for the second step, we're going to take the solution from the previous step, which is this one, and then plug that back into our time advancement matrix. Okay. Plug it in to the phi ends. Okay. And so just to kind of save myself the writing, I'm going to go ahead and come back here. Okay. And so now this is going to be on the second time step. Okay. Okay. But instead of having all zeros here, I'm going to plug in the solution that I got from the first time step, which is 1, 0, 0, 0, 0.5. Okay. All right. And so this changes things a little bit because now we actually have to multiply that matrix right there. Okay. And so if we multiply that matrix, what we get from this is the following. Okay? And so we multiply this matrix by that vector, and then we add that vector. Okay? And then we end up with phi I at time step 2 is equal to 1, 4.8, 0, 2.4, and 0.5. Right, and so that's how you advance this forward, 2 time steps. All right. Okay, so that's all we got time for the review. So hopefully that was useful for you guys. And so, you know, best of luck studying for the exam. You know, as always, you know, if you have questions about anything, please don't hesitate to reach out, and I'm always happy to answer questions, right? And so best of luck for studying, and I'll see you guys next week.